Okay, my audio should be connected now as well. Yep, looks like the little icon is moving. Where I'm at, I don't have enough, excuse me, bandwidth to do video and audio. And so since I'm nervous about competing not only for that, but also with bandwidth for slides and drawing, I'm going to do the audio on a regular phone call, and I hope that's okay, guys. So I have my chat window open, and I will keep it over to the side just to make sure I'm keeping an eye on things in case you need to tell me that it's going off the rails. Okay, we had made it up quite a ways into this. No, we haven't gotten that far. Right here. We were at the beginning. I take it back. I remember exactly where we were. Okay, I think we are ready to go. So what we talked about so far in this chapter is we talked about LANs and how a LAN is a collection of devices that can see each other. And so one of the things I taught you early in the semester was to think about routers not as devices to join networks together, but as a device you place in a network to separate it into two pieces. So it will break a LAN into two parts. And if you put a router in between, left and right side, the left side can never see any of the devices at layer 2 on the right. It's on a separate LAN. You can only see things on your local LAN. Therefore, the router has to be on your LAN or else it can never see any of your packets. And in fact, the router has to connect to every single LAN that's out there. So if the router has 10 ports, it's going to have a connection to each one of those LANs. Then we finished up last time by talking about virtual LANs, where you can teach switches in an organization how to take people who aren't physically located together but are connected to the same switch infrastructure and get the switches to simulate what would happen if they were really on a same LAN. So what does it mean to be on the same LAN? It means you might see everyone's broadcasts. It might mean you send something out, only they can see yours. It might require that ARPs and all the other types of layer 2 messages that are generated are only seen and distributed among people who are part of that VLAN. So we have this VLAN ID, and the switches all keep track of it in a particular organization, and it's extraordinarily effective and incredibly popular. So it's a dominant way of defining what scope people have. And a really interesting phrase that makes a lot of sense is to look at the devices that are on your LAN or the extent to which your LAN extends by considering the broadcast domain. And this is the range in which, if you were to send a broadcast message, how far would it go? Who would see it? So this switch VLAN concept can actually be tunneled through routers. It's very, very effective. So at any rate, that's one thing. Today we're going to start off by looking at another one called multi-protocol label switching. And this one's a commercially available product that's a layer 2 type of product, and kind of like VLANs, where you change the standard a little bit to kind of shoehorn in some identifying numbers so you know what label this particular packet belongs to. This allows you to define groups of people who are kind of like on the same LAN, and I'm fighting a cable here, forgive me for all the reaches across, but who are maybe on different sides of a telecommunication carrier network, like all of the offices on Xerox's network worldwide. They would all be possibly connected together with multi-protocol label switching technology that sits on top of some certain speed point-to-point network. So what MPLS does is it gives you the ability to define groups across these organizations by the MPLS tag or the MPLS label number, and then share that with the carrier, share that with the phone company or the internet provider, and they will program their switches to deal with these labels as well. So if you define that different groups are sort of homed into certain places around the world, and a packet is seen on this network that's got the same label that says it belongs to the accounting department, then instead of having to run a physical circuit to the accounting department and one here and one there and one there, what you basically do is just connect in the middle. So this is a great way to reduce expense. So I'm going to draw it out in a little more detail here. I got to shrink this window because WebEx needs a little bit for its little banner at the top that it's showing me to control what's going on, but it interferes with my Sketchpad. So let's say you have offices with users on the side over here, like branch offices here, Tulsa, Monterey, Houston, San Antonio, Austin, and Dallas, right? Kind of close by, oil patch kinds of places. And then you've got, 3 sort of main offices and the internet over here, so an ISP. What you don't want to have to do is, if this one is, say, distribution, and this one is the accounting and head office sort of stuff, and this other one might be, let me think of a decent example, the field management, your big, not so much a warehouse. What you don't want to have to do if you are building this type of network is to have to build, one set of point-to-point circuits here, and then have to duplicate that around, to all of these others as well. You don't, oops, messed that one up. So that's something you don't want to do. What you may also not want to do for efficiency purposes is you may not also want to pick one of these guys as the winner. So everybody runs to them, and then you have to connect these guys together in some sort of way, because it may be that, this guy, let me get rid of this. If you have a traffic flow that needs to go from here to here, or if you have another traffic flow that needs to go from here to here, drawing it through this hub and spoke may be an incredibly inefficient way to pull it off. So we need some sort of technology that is not the internet, so people can't see everything we've got going on, but nonetheless is packet-oriented and shared, because you also don't want to have to pay for all those circuits yourself. So what these providers do is they put these switches all around their network in all kinds of different cities, and what everybody does is they just connect one time with a pipe of a certain size, whatever they think they might need, to whichever one of these things happens to be closest. So say the Houston one needs a really big connection, San Antonio not much, Austin needs a little one, Dallas needs a slightly larger one. And you do the same thing all the way around the network. This one, I have to be careful here. This one I didn't have to buy. The ISP already bought their own connection to this MPLS cloud. And what I did have to buy were, the ones from my other field organizations here that I was doing. Now it's time to build connections. So what I do is I define on a web page an MPLS label, and let's say it's label 1. So anything that this network sees that's label 1 knows it needs to go to the accounting office. So here comes some packets, and what they will be is like a virtual point-to-point circuit, but I never had to buy the virtual circuit. Why didn't I have to do that? Because the phone company already took care of connecting all of their switches internally to each other, and I never had to do that. And this is a full mesh, even though I don't show it that way. And whatever sophistication they may have it built hierarchically, it's invisible to me. It doesn't make any difference. All I know is that if I tell this network I would like a 64K circuits worth of bandwidth between Houston and accounting, and it's going to give it a VLAN ID of 20 over here and 1 over here and 13 over here, then each of these can have different speeds, and they can manage that. It's extreme flexibility. And over that same physical circuit that I bought over here, I also now can run another PVC down to the internet. And so can this guy. And these can be different PVC IDs, 2 and 21 and 14, I guess here. And they can be different speeds. As long as all of the PVCs in any one of these connections doesn't exceed the physical capacity, then you're fine. This is a lot less expensive than having to run one, say, directly over to here, almost certainly. And it costs you more for this service, so you'll pay something for shipping these packets through, but this is an extremely effective way. And let's say if you decide you need to start sending some packets because of a research project to the University of Houston over here, then you don't have to worry about building a circuit to University of Houston. You also don't have to worry about paying for University of Houston's connection to MPLS network. They already have one with tons of other PVCs from other places coming in. You just have to both agree and both log on to your management web portal and agree to put one in between the two of you. And maybe this is 128 kb per second. Presto, you're done. No installation time, no circuit, no physical circuits to build. A change to routers on your side and a change to their switches, which can be automated through a portal, and you're done. So as more and more people join these types of networks, it becomes used. So why do this? It's great in a metropolitan area, but it's used worldwide. Why do things like this? Because it's more secure. It's not shared in the middle, in that it's all one company building it. If AT&T and Telmex decide to connect their networks together, they're going to do so in a very careful, structured way to guarantee the bandwidth is not changed. You can offer different levels of services. You can offer redundancy. You can allow traffic shaping. I want some of it to go here, some of it to go there. A lot richer sets of rules, and you're willing to pay for it. But it is different than putting it out on the Wild West internet. Okay, so this is sort of a building kind of an overlay network for people that don't really want to build the entire thing themselves. So very popular way of building out institutional networks that cross geographies, sometimes even on different parts of the same city. It's cheaper to do this kind of stuff. So we designed, oh my gosh, millions of millions of PVCs, millions of destinations of these things when I was in charge of the design team at AT&T. So we, for our region, we did lots and lots of this stuff. A lot of fun, really interesting, good to kind of get good at. So what you see in here is all you need to do to kind of let the switches and your router knows if your router sees that you're trying to get something from a source IP address that you've been assigned through a tunnel to the accounting department back over to the accounting department, the router will have a rule and it will insert into the packet an MPLS label at layer 2. And the phone company equipment will see that label. They'll see it's coming from you on your physical circuit, and they'll know exactly where it needs to go. And they'll know what speed and what type of guarantees they've placed on it, and will act accordingly. So this has grown into a very mature type of solution, barely touched on by the book, but this is a type of thing you'll run into. If it's not MPLS, it can be any of a number of others, but you could even have just them hand you an Ethernet circuit, but you could still have labels on it, for example. VLAN and MPLS are somewhat interchangeable conceptually, but this is what you're going to run into in a larger business. Okay, you're not going to run everything over the internet. That'll never happen. It's too risky. No one to call if you're having trouble. There's lots of restrictions. You'll put stuff over the internet that belongs over the internet. So these routers have an extra capability. They can understand labels. They can assign labels based on IP addresses. The MPLS forwarding decisions differ from IP. So here's a big advantage to the phone company. If you're using all 10.private addresses because you're going amongst your own offices, you're not going over the internet. Why would you NAT it? Why would you change it? If you're doing this all over, among your offices and you're using 10 addresses, then what happens if the phone company has another customer that also wants to connect to the MPLS network and they're using the same ranges of addresses, which they all will be, all of them. They will all be using 10 addresses more often than not. How do you keep those from conflicting with each other? Well, just don't pay any attention whatsoever to the IP address. Just look at the label at layer 2. So the routers from the customers have to add label numbers at layer 2 to every IP datagram as it enters the MPLS network, and the switches from the phone company inside the MPLS network ignore the IP addresses. They are layer 2 label switching devices, and therefore there can be no conflict at layer 3 if you're never paying any attention to it at all. So it's a brilliant solution to that. It's really smart way of doing it. So MPLS versus IP paths, you can do multi-paths. You can add labels and rules that say, you know, across this phone company Blue network, I want you to go a different route to get to A, depending on where it's coming from. So this solves a big problem with just IP-based routing. With MPLS, you can add some sophisticated rules to that. Signaling, you can build these trees and support higher layer discovery protocols like routing protocol discovery that would be required to run Dijkstra's algorithm or Bellman-Ford types algorithms. You can use a special type of signaling in MPLS that accomplishes the same goal, that starts and stops labels. This is how you can just go to a web page and cause labels to be built without having to deal with a bunch of paperwork. So they've made and automated all that. In fact, you don't even log into a web page. You just, all of that's pretty much automated at this point. So if the server that you're assigned to this afternoon in AWS is one out of Pittsburgh, then they need to provision an MPLS tunnel instantly all the way back to the circuit that you use to connect to Amazon's cloud in Houston, you know, for example. So there's signaling that's done, different tables at different switches, but basically you can see they're dealing with labels, not IP addresses. So if the N label is 10 and you're trying to get to 6, then go out interface number 1 if you're trying to reach A. If it's coming into this switch and it's coming from PVC of label 12, all of this for one customer, it's going out, then send it out label 9 if you're trying to reach destination D, and you'll get label 9 via destination 0. So I'm going to change the destination label address to 9 in order to reach D, and I will send that over circuit 0 so that it goes, you know, to the next party. So you'll build this for every single customer that you have. You'll have separate rows for each of them. If you ever decide to exchange things with another customer, like that example where I decide to share something with U of H or to an internet service provider, that's an example, then both of you have to submit technically a legal contract to allow your two PVCs to connect to each other. And then you got to be careful, because now you've got a PVC on your network that's like bringing traffic in from the internet. You don't want to just dump it into your network, trusted like it is from all of your branch offices. Well, what would you normally do with that traffic? You would inspect it. You would put it behind a firewall. You might prevent it from getting inside your network. You're still going to do all those things. MPLS is just the delivery mechanism at layer 2. You don't forget about security. You will bump it up to layer 3 and still deal with it the way you always have before. You know, maybe you only let them get to your web page, for example. All right. So that's MPLS. That's a layer of layer 2 networking that is an example of a very popular approach in industry, and one that is sold and managed by the carriers, by the public providers, the phone companies of the world. What we're going to talk about next is data center scale networking, and this changes so quickly that it's a little bit funny, but funny ha-ha, because it's gotten incredibly complex. Data center networks can have hundreds of thousands of individual addressable hosts, and lots of them can be on, lots of different IP addresses can be on a single host if it's running lots of different operating systems. So host doesn't always mean physical devices, but in this slide, that is what they're talking about, are kind of the physical devices. So you can have people that build these cloud scale centers and then let other people in, or they can run it just for themselves. You have people like Google who run their searches on servers in this type of environment, Apple's iTunes music store, Netflix's movie downloads, Dropbox's networks, destinations, their storage systems, all of those things run in the cloud. So you've got some applications that need millions of users, and you have millions of applications that need a few users, maybe even one. So how do you sort all this out? How do you keep this going? And how do you avoid some of the bottlenecks? Well, one of the ways that we learned to do this was by building a hierarchy in a data center. And in the old days, what we used to be able to do was kind of isolate things on sort of one side. So you put servers over here, and you put all the big storage arrays and the other servers here, and you'd connect them together with a high-speed switch. And I mean, we're talking like super high speed. And these things would stay sort of together because these apps that were running here were looking for the data that was running here. So they were on their own sort of area of the network inside the data center, and that was great. And then you could have other classes of applications, and maybe these went out to the internet a lot more. And so they had their own switch. They could talk to each other, but they could also get out to the internet. The switches interconnected with each other, but there wasn't that much interaction between the two. When we began to use virtual machines and genericize the type of servers, they got very, very powerful. We wanted to run lots of things on them at once. This model blew up. And what we got to instead was this one, which is the servers all look the same. They are all connected at the top of a rack to a top of rack switch, a TOR switch, a TOR switch, a pair of them usually. And they then connect upstream to another tier of switches, and it allows traffic from any server to any server at full speed. So you build up your infrastructure significantly on the network side here at switch level and allow massive traffic. And it's evolved from here as well. What it really looks like now, which would have been done in the first place if we had the technology to do it fast enough, is you have one core like this. You don't have multiple layers. You have spine and leaf. So you can have data flows anywhere, any pairwise inside of here, and you don't have to climb your way up like these slides suggest. So here I might get out, something comes in from the internet, it goes to a load balancer that makes the decision on which server to hand it to, and it goes on assigned to a particular server. The load balancer might split that across a couple of others. You may send the answer back from one. So this sort of rich interconnection, this mesh that they're showing on the slide, that's been a little bit somewhat replaced. But here's a snapshot of a set of racks in Google's data center from 2012, and it's a little difficult to see, so I'm going to zoom in for you best I can. These are all servers. Each one of these rows is a server, and on top you have switches, maybe Cisco switches, maybe someone else, but that kind of switch, and they're 24, 48-point enterprise-grade data center switches. So they have the ability to handle the traffic. It looks like they're assigned to 3 racks per pair. And these are redundant, and so each one of these servers connects to both of them in case there's an outage on one, and the traffic goes uphill from there into fiber arrays and to other switches perhaps, and maybe you've got a little bit of a hierarchy going on. So scale is quite dense. Imagine this times 50,000, if you will. And I want to see if I've still got a picture. I do. All right, so I'm getting to something else that's kind of interesting in here as well. So what this has let us do is drop the bottom out of the cost and out of the delay for getting things done. So you can see over time the number of operations per second and the latency of RAM. These things have parts where they cross. You will find it's cost effective to invest in crazy expensive memory if it keeps you from having to buy more servers. We talked about that a little bit before. So there's some URLs down here if you want to kind of go and dig in and intrigue, and if this intrigues you and you want to ask, want to understand a little bit more about it. I don't think I'll have a homework problem on it for you though. Here's a typical layout of a large data center. The front half is all storage, and you'll have basically individual cabinets for particular users. You'll have big arrays of batteries that power the system. you've got air handlers, heat rejection devices, basically that will suck heat out from your converters. You have generators with big diesel tanks that sit on the side, and you have power distribution units. Think about them as commercial grade circuit breaker boxes where you have the ability to turn your lights on and off, except these are on the floor and the lid lifts up and it's horizontal, parallel to the ground, not vertical on a wall. And you also have air handler units over here that are different than they've ever been, because these usually you usually think of these as heavy refrigeration units, but not anymore. Data centers aren't cold anymore. We've told people, don't build equipment that has to be chilled like that. Knock it off. Just build equipment that can radiate into the normal air, can take room temperature for humans. Don't make my people walk around with a fur coat on all the time. So that's changed a lot over the years. These battery arrays are pretty interesting. They're usually, in most of the centers I've seen, certainly in all the ones that I was responsible for, you have these big glass tanks that look like you might have a brain stored in formaldehyde or something, except they're much bigger around than that. And you have cells in them. That's basically battery acid, and the cells are what allow you to store and retrieve back energy out of them. But they're kind of open on the top. Air can escape. There's lots of fumes that come out of these things. So it's a highly toxic environment, and there's a room of maybe 800-900 of these things, and maybe 300-400. It's massive. It's a farm of them. And you have these big metal buses that connect all of them together, one into the other. Data centers often run on DC, depending on the type of environment it's in. They don't run on AC, so yes, you build servers that have DC power supplies. That's all the power supplies in your computer does, is convert everything to DC anyway, so might as well get rid of those and just hand it DC to begin with. So that's the way the phone network's always been built, on negative 19 volts in DC, for example. So these batteries are built to do DC anyway, so that's what they do. I remember a guy dropping a wrench, a crescent wrench, in one of these things. Had it hit the acid, I don't know what in the world would have happened, but it hit the bars and cut across the bars on the top and vaporized the metal, just to give you an idea of the amount of energy that we're talking about. So it'd kill you instantly if you touched one of these or fell in. So they're very dangerous environments, but this is how you keep the power conditioned, because the commercial power that comes in from the electric company is usually crap. This is why people try to get you to buy power surge protectors and things like that for home, which is a complete total waste of money, by the way. But at a data center, that power may not be smooth, so you'll run everything through the batteries to kind of even it out and give yourself a perfect constant voltage. And if the power goes away, the batteries can run for a while, fire up a generator within 15 seconds, and switch that as your commercial source, and you begin recharging the batteries, and the power continues on through to the servers in the data center. So it's quite an interesting tour if you ever get a chance to take one and sort of try to draw and piece it all together. You do get better power delivery efficiency. There's been some decent papers written on why that is. You get rid of some of the equipment and some of the conversion, phase converters and things like that in here. The power distribution units are simpler. You have less gear. So power delivery improves, the efficiency if you do this stuff with AC versus DC and getting it through. So I don't remember exactly how to walk through all of these, but for a 380 volt DC architecture, you take AC in, 480 volt commercial, and then this is 97% efficient. This becomes 93%, 86. So overall, you preserve 76% of the power is available for your loads, and very much less is consumed by the devices along the way. Whereas without a lot of efficiency, you can waste half the power by having it consumed by all of this garbage in between, like fans and things like that, instead of actually performing computing, which is really what you want the power to do, is you want the power in the data center to reach the computers and perform computing. Okay, so Google has a distribution efficiency target of a really high rate. I don't know why I don't have a URL in here, but at least thank goodness I have the reference of the stuff I went and dug up and looked. And so, what they're basically showing is how much of the traffic they are able to hand off to load. So a company that big, they'll track that, and they'll make someone's job dependent on moving that number up or down, whichever direction they're basically trying to look at. fresh air intake is the way newer data centers are built. You'll pull in fresh outside air. You'll test it for every contaminant known to man, combustible molecules like gas vapors, poisons. What are some of those white powders that people used to mail around to each other to cause problems? And so you have systems that test for all that stuff in real time, and will shut air off and just recirculate instead. But on a cool day in Dallas, AT&T will pull outside air in, filter it, and run it through their data center. And they'll let convection deal with most of this stuff. And they'll send exactly the quantity of air that's needed down each aisle for each rack based on the computing and the heat generation that's going on right now. So these are very closely coupled, computer controlled. It is not like you turn the fan on and just let it run all day long. You send exactly what's needed. And these are sealed types of systems where you waste nothing cooling any part of the data center that doesn't need cooling, right? So that's come a huge way with just high sophistication. What this basically shows is you can design your system with a raised floor and then have hot and cold designated aisles. It turns out if you concentrate the heat in as small a space as possible, then your air cooling systems are enormously more efficient at using energy. So what you'll do is take two racks and put them back to back and have the heat come out the back of both of those. But like I said, in more modern data centers, the stuff runs at room temperature anyway. Here's a different way of going about this. What Google does in this data center is they have these containers, the same ones that you see on trains and on the back of trucks and on ships at sea. They build their computing infrastructure a container at a time. So what they get is a container. These have a door in them, which I think is rare these days. I don't think there's a way to go inside most of these anymore. Putting a door in implies that you can go inside and do something. Well, what Google will do now is put so many servers in one of these and build it out of such flimsy, thin metal that they're never intended to be moved or pulled out, or you just don't even put that much metal in it. So you can cut thousands of pounds of metal out of each one of these containers, which really, really adds up, and lots of cost out of them as well. And what happens if one of them breaks? You shut off its power, you mark it off the list for network, and move on. They're all the same. So if you lose a few in here, you're taking the redundancy approach instead of the reliability approach. You will not go inside and try to fix it or replace it. Once a third of them have died, or you've got newer systems that can save enough power that it's worth reinvesting, the claw will come and pick up this container and replace it with another one that's got newer, faster, cheaper, cooler equipment. And you just do this Lego block by Lego block, but each one of them has 3,000, 4,000, 5,000 servers inside. And you have hundreds of thousands of these around the planet. So it looks nothing at all like anybody else. The big data center providers like Google and AWS and Microsoft, they do things different than everyone else on the planet. They're not out buying Dell computers and Cisco switches and the same types of batteries and fans and cooling fan trays and coolers and things like that. It's all custom built for these guys. It's a different kind of world. One of the things that's not talked about in very many of these textbooks, there are some on data center computing specifically that do a good job about talking about this stuff, that I want you guys to understand is something put forward by an organization called the Green Grid. And some people I know that I used to work with went to do some of this work. And the Green Grid is sort of like getting interested in the same types of efficiency ratings that LEED gives to buildings. I don't know if you've ever heard of LEED, but you can have a LEED silver or LEED gold building, and basically you are being honored for building it in as energy efficient manner as possible. And there's some crazy energy efficiency stuff that's done. Not to get off on a sidetrack, but when I had Nissan as my customer in Franklin, Tennessee, where they had a large manufacturing plant where they built vehicles and built batteries for the Leaf, for example. I had a battery plant there as well. In their headquarters, they still had people that were desk huggers that would have all their junk on their desk, but they were moving rapidly towards a model where when they knew who was coming in, you badged in, they would assign you a floor. And there would be shared types of office spaces of different types on that floor. You know, if you're a manager, maybe you get one with a door. And if you are just a teleworker, maybe you just get a counter at a bar seat, kind of like you might at Starbucks or something. But you get a space that's appropriate based on the type of work that you're doing. And they'd have some shared resources like printers and things. But they would put you on that floor because the rest of the floors, they don't bother turning on the lights. They don't bother cooling them, except at extremes, or heating them. And they don't heat water for the sinks. They cut off electricity to the coffee machines, and maybe they do something different with the vending machines and so forth. So they cut everything out. They can basically turn part of their building off. And when they see one more person coming in, they may adjust the airflow a little bit. They may add a little more capacity, start up another small micro chiller to deal with the extra heat that you are likely to generate. So total sophistication. And we had engineers that just specialized in helping customers build out and implement that stuff, including only turning on network ports on network devices that had people that were at work that day, and turning, you know, the rest of them off. The network equipment is notoriously bad about being the biggest energy waster because they always have to be on, and there's always packets to route, and there's no way to save energy. There's just, you know, how do you turn part of a router off? Well, so you get very aggressive about the equipment at the edges and use things like switches instead. Right? So that's another reason why they're popular. So what the Green Grid does is they're worried about same kinds of similar things, but they're worried about what's going on inside of a data center. And they're trying to give you metrics and tools that you can use to calculate the amount of power that is coming into your data center that's actually being used for running computing versus all the other extra junk that you have to do, like power the space heater under the cold secretary's desk, or keep the vending machine running, or the coffee maker, or the lighting, or the security guard's desk computer. And all of that is required to run the data center, but none of it performs useful billable compute cycles. So let me see if I can get any of these to open up. It doesn't look like they're going to do it. Let me see if I still have a presentation out here. Oh, I do. Yay. I managed to steal one. Awesome. Oh, I remember this. What I will do in the meantime is close this because it's using cycles. It's going to let me change the window size. Oh, it will if it's in front. So PUE is a important metric that was put forward by the Green Grid organization, and it stands for power utilization efficiency or effectiveness, forgive me. And what we wanted to do was set some benchmarks that said, you know, what proportion of the energy are you actually using to do computing versus, you know, wasting. So I had a lot of government support. There were some other industry groups around the world. And we wanted to be good citizens of the planet and try and use as little energy per compute cycle as possible. So in the U.S., we achieved consensus on what to try and tackle for PUE and set targets for customers based on data center size for what their PUE calculations ought to really do. So let me get in here and show you the definitions of some of this stuff. You can have a PUE for container that we saw a picture of, for the cooling system, for power delivery. You can have one that takes into account what's going on within the entire facility or just within a certain boundary in the facility. So here's an example of a calculation where I have 600 megawatt hours coming in on the top left corner of my diagram, and between what my transformer eats up and what my chiller eats up, what I have going into this container is 475 megawatts going to the IT equipment itself, another 25 megawatt hours managed by or eaten up by the uninterruptible power supply. So I'm got a PUE of 1.26. Of the container overall, which lets me add back in the UPS in that zone, I'm much closer, 1.05, for example. So that would be great if you could get those numbers down. So the lower the numbers are, closer to 1, the better off you are. Here's an example of where I had 2 different zones. They have the same chiller power, but they don't have the same IT equipment. So they both have to use a 200 megawatt hour chiller. One of them does it to power 1,500 megawatt hours worth of equipment, the other one only 500. Very different PUEs. You average it overall, and this center has a 1.35 PUE ranking. So N is for non-IT power, and I is for IT-based power. There used to be some amazing metrics. One of the things that the people responsible for this type of initiative at eBay used to do, and I don't know if I still have a chart on it. God, it would be cool if I managed to squirrel that away as well. eBay dashboard. Let me see if this will really do it. I don't know if I still really have it or not. Let's see if this opens it up. It'll take it a minute, so I'm going to continue on here. One of the things they did at eBay is they did things like calculated how many bids, how many auctioned items per kilowatt hour of electricity was I able to do this week. How many kilowatt hours of server CPU time did it require to list an item this week or to sell an item this week? How many bids an hour can I manage on a single server? Totally different way of looking at what's going on, but it directly connects the IT organization's normal careabouts with the overall business careabout. So in a hospital, it might, like the Houston Gulf Coast Regional Blood Center, which is who manages blood donations in this part of the country. What if you, as an IT person, were measured on how many kilowatt hours do you consume for every bag of blood donated? That would be a totally different way of looking at your job, but it would get you very, very closely connected to the business. So what eBay did was they generated this dashboard, and it doesn't look like I've got pictures of it. What a loss not to have grabbed that correctly. Let me see if it's still out there. I can't believe it would be out there after a handful of years, but yeah, it's not there at all. So, dang it. And I knew a guy that went over there and sort of helped run that stuff for them. Let's see, eBay Energy Carbon Dashboard. Let me see if somebody else has squirreled it away here. Oh, Data Center Knowledge has it. I know they do. And you go, this is it. Okay. So probably what I do is save this, huh? So this is their DSE ranking, and on the left they have the infrastructure guys, and on the right they have the business guys. And what they're looking at is transactions per kilowatt hour. So that's the overall business, and they track buys and sells by a kilowatt hour of energy. And you can click on these and look at different quarters. This used to be up for the longest time on their site, and then I think they got a little cold feet about it. So for the infrastructure guys, they get measured on things like PUE, workload utilization effectiveness, and a couple of other metrics here. Power load, how many servers, how many active users, what percentage of my energy is my own clean energy, solar, that sort of stuff. On the business side, how much money are we making per user? How much carbon are we emitting per user, or overall, how much are we able to offset? What is our per megawatt revenue number? Well, $337 million of revenue per megawatt of energy that's pulled in an hour, for example. So interesting, totally different way of looking at this stuff. Very groundbreaking, very influential in the industry. I went to lots and lots of customers and built these types of dashboards for their business as well. you know, and if I had had the Gulf Coast Regional Blood Center, that would have been one of the metrics I would have used. So PUE is a way of sort of figuring out how effective are you at delivering the resources you're consuming to the task at hand. Somebody else can worry about, once you get that power into the CPU, how do you make the most efficient use of it? But this is, you know, a little bit different. So networking is a huge piece of these calculations. We've been horrible at this. In 2006, the vast majority of data centers had a PUE of greater than 3.0, which means for every unit of energy that you consume doing computing, you wasted 2 others, usually one cooling it and one dealing with all the other people overhead. So only 5% had a PUE of 2.0 or better. And at least then you're using as much power for the mechanical and electrical systems as you are for the compute systems. But the last time Google reported PUEs, it was in the 1.1 or so, 1.06, if they had been a little less hard on themselves with the way they define things. So they were crazy good about doing that stuff. And one of the things that we can do to look at our networking efficiency here is to see if we can find anything more recent that they've done. Okay, so they're showing what's going on here. Yeah. So here's their quarterly PUE and the trailing 12-month. So depending on the season of the year, they're going to use more or less. In the last and ultimate 12 months, they used 1.11. And here's the various campuses. Their leading one, it looks like, was in Council Bluffs, Iowa. No, Dallas. Oh, the Dalles, excuse me. That one uses hydroelectric power. The Dalles is right there off the locks in Oregon. Been there before, and it's also new ones. So the newer ones do better. They didn't have data for, looks like, last year. And I'm sorry, this is in Spanish. I didn't ask for it that way, but Google thinks it's smart and thinks that's what I speak, and so it just, you know, whatever. Like, thank you very little. And here's what that looked like at the time. That hasn't really changed very much. So how good are we now? When the Uptime Institute, you know, looked at over 1,000 data centers, most people are in the 1.6 to 2.0, 2.1 range. I will tell you, unless you walk into Google, Facebook, Amazon, Microsoft, or someone equally as IT-centric and large, you are very likely to walk into a data center whose PUE sucks. And so anything you do networking-wise to kind of concentrate and re-architect the way they approach how they core up their gear is going to affect positively the PUE on there. Okay, are we ready for the most important kind of walkthrough of the semester so far, which is going to be to see if we can figure out what happens in a day in the life of a computer. And I'll tell you guys, this is my very, very favorite part of this course, because if you paid attention, you'll know the answers to this. So let's say our goal is to identify what happens when somebody opens up a particular page on the web, let's say google.com. And it's one of you, and you attach your laptop, you come into class or come into campus to the Student Center, and you open up your laptop and you connect to the U of H wireless network and go to google.com. Exactly what happens from a network point of view on your system and on the network. So let's say we've got a scheme like this. I have a remote DNS server, and let's say you use Comcast to, once you leave U of H, they have a contract with Comcast. So the packets that you send out go through Comcast routers, and Comcast has one of their routers in one of these Internet Exchange Centers that we've talked about a bunch of times. And so there's a place they can exchange lots of traffic with Google's backbone. So Google also has a router that's on that inter-exchange center. Let's say it's in Wilshire Boulevard in Los Angeles. That's the most expensive one that I know of on the planet. And that's where Google's web server sits. So here's their overall network mask and network number, and here's their web server. So, you know, what goes on? You're going to open a browser and you want to get a web page, right? So that's the idea. So what's the first step? Well, the first step is you try to connect to a Wi-Fi network. You listen for a beacon, and if you see it, you connect at layer 1 initially, and then you begin to ask for the things that you're going to need as a user of the network to get this going. And let's say for this network, I have DHCP running in the router. So it's been given a batch of IP addresses and the permission to hand them out. Okay, so I need an IP address. So I'm going to generate a DHCP packet. It runs over UDP, and it gets to the IP layer. It assigns my source address, and the destination address is broadcast because I don't know who runs DHCP. It goes down to Ethernet. Ethernet gets in on the act. They know the source address, but they also broadcast it because they see you don't know where it is, so how would they know where it is, right? So there's no way to ARP for broadcast. It basically needs to be sent to everyone. So you'll generate out a packet. You're going to build that on Ethernet, and it'll be broadcast out. One of the people that will receive it is the router. They will extract all of the headers off of it, work their way back up to the top. They will see that there's a DHCP packet in there. It's a DHCP request, and they will answer it. And the DHCP software will go to their pool of addresses, give one to you, and they reverse the process. Now, this time when they send something back, the switch has been paying attention, and so now the switch knows where both of you are. And if you send something to the router's hardware address again, it'll know exactly which wire to send it down and which ones not to send it down. So this time I'm sending something back to your hardware address, so it's going to be sent only to you, and you will decapsulate DHCP, and now you have an IP address. You also know a bunch of other stuff that was built into there. You know the network name, the DNS address of the DNS servers, the address of the first hop router, and some other things. So I'm going to try to pull up my network panel. Let's see if this will pull up for us. And here's my IP address. I've also been given my subnet mask. I've been told the router's number in IPv4 and IPv6, and I have IPv6 addresses here that can be used. I obtained this address using DHCP, and I didn't really need a DHCP client ID, but if I had, it would have gone there. I've been given a single solitary DNS server address, which is the IP address of the Wi-Fi router here that I'm using, so it probably doesn't run DNS really. It probably just takes that DNS request from there and just forwards it on to one that the telephone provider provides. And then this is the name of the domain that I'm in, so if I try to go to a web page and I just type in like Bob and hit return, it will guess bob.hitronhub.home, for example, and so forth. And I see my hardware address back here as well. So you can find this stuff by using some system utilities and digging around. So what's next? Now I have an IP address, and the user, it's the user's fault all this happened, of course, because the user opened the browser and typed in www.google.com and hit return. So maybe I would have grabbed my DHCP and my IP address automatically without them doing anything. Can't blame that on them. But everything else that follows is their fault. I would not be doing this slide if they had not opened up their web page and asked for a packet to be sent to Google. And in order to send it to Google, first I have to figure out what is that server's IP address. So I send DNS out. I get part of the way down, and I realize I've been given the name of and the IP address of the DNS server, but I don't know the DNS server's hardware address. And remember, I'm going to DNS to get the IP address of Google. I have the IP address of the DNS server, so if I just ask the DNS server, what's the address of Google, it will give it to me. But I can't even do that without being able to send it to the DNS server in the first place. So the DNS server my DNS client issues a request. It goes to IP. IP realizes, oh crap, I don't know the hardware address for this DNS server's IP address. So we use ARP. ARP goes across the network. You send your request out to everyone. It's broadcast to all devices on the LAN. The router answers and says, if you're trying to reach that IP address for the DNS server, I've been told to answer on its behalf. So please send it to me. Now, there's a couple of ways it would know to do that. One way it would know to do it is if it's running DNS. The other way it would know to do that is if it sees the IP address you're trying to reach is not on the local LAN. It's on a subnet that the router can reach on a different LAN, via a different LAN, in which case it will also respond to this ARP request. That's what happens 99% of the time. The packet that you're trying to send has an IP address that's out on the internet somewhere, and the router sees that, realizes you're going to need its help because the subnet you're trying to reach isn't on the local LAN, and so it tells you to send it to him. So he will respond back with his own hardware address of the port on the LAN that faces you, the requester, not the port that faces the rest of the world. This arrow or this, whatever this shape is, makes more sense to me had they drawn it to point exactly to that port. So now it does. Okay, so it's going to respond back. Oh, told you to stay over there. It's the next slide, so what can I do, right? Okay. The ARP reply comes back. Now you know the IP, the hardware address that you should send something to if you're trying to reach the IP address of the DNS server. Again, you now know the hardware address of the router, and if you will send your DNS request to the router, it will forward it across the network to Comcast, which is where the DNS server is set from our earlier diagram. All right, so I build my Ethernet frame inside it. I have a source and destination of my laptop and the router. Inside of that's an IP datagram, and the source and destination of that is my computer and the DNS server. And so I build a DNS query. The IP address of the DNS server is matched up with the hardware address of the router. So this time it will leave. The router will get it. It will drop it onto the next LAN. So it will come from the router's hardware address to this router's hardware address and ultimately make its way to the DNS server. It gets up to the top and it answers the request. What is it being asked? What's the IP address of the web server at Google? And it knew how to get from that Comcast input router out to the DNS server, which was sitting behind a different router on Comcast network, the same way that my router knew how to get it over to Comcast, because they exchanged information using a variety of routing protocols to get there. So to send my HTTP request, which is what I've been waiting on all the time, now TCP can continue on with its task. It's asked and then told the answer to the question of what's the IP address of Google. This one was really lucky because the DNS server at Comcast knew what the answer was. If it required iterative or recursive DNS hunts, that would have been a totally different thing. But before it can send the HTTP, it's still waiting. The user is still waiting. It's still their fault. I have to do a handshake. So I send a TCP send segment. I get a SYN-ACK back, and TCP answers with SYN-ACK. That makes its way back to me, and I'm now ready to send data. I can actually send data in the third part of the handshake. Our book doesn't teach us that. They don't show us examples, but you don't have to send the ACK back and then send another packet. You can use that last packet, and you can load it up with data. You can start doing everything with the SYN-ACK. So I send the data over. That data is the HTTP request. It gets forwarded over to that server through the network. Once inside the server, it looks at the port number and it matches it up to a socket and pushes the data across the socket. It makes it up to the web server, and it responds back with HTTP with the web page. Can you believe that? Now, if you paid attention this semester, you followed every piece of that story. If you didn't, or if you have some weak spots in there, that's what you'll want to be able to dig in on and work on. I will very likely give you a question like this with a ton of different steps or a ton of different hints, like a packet is seen on the network with the following Ethernet address. And I may have another one that says a packet is seen on the network with the value of the DHCP protocol set to reply. And you got to figure out which one comes first. I may give you 15 or 20 of them, and you got to figure out what's the right order to put these things in. So you will need to practice with this scenario and make sure you kind of understand what's going on. And I would recommend pulling up Wireshark and looking at examples of each one of these types of packets. That would be my recommendation. So I was a little late putting the recording from Monday up. This one is a very standalone lecture. So if you're listening to this recording, and this is really aimed at the Tuesday people, they can listen to this first and then listen to the other one second. That's perfectly fine. So we've wrapped up chapter 6, believe it or not, and it's the last core chapter in the material that we've got. We've got some homework stuff to pump out. I've got 2 homeworks, one turned into 2, and I'm cranking that out after the lecture. And so we really learned a lot about where much of the action actually takes place in an institutional network, and that's at layer 2. We learned about cleaning up after your own messes with error detection and correction. We learned about collisions and how Ethernet backs off, and it's a hint as to what's going on upstairs. We learned that even at Ethernet level, it keeps a copy of the last frame that it sent, so it's a little bit of sort of a window of size 1. It's a little bit like windowing. We learned how addressing works, Ethernet. We looked at AlohaNet and University of Hawaii, and we spent some good time on LANs, VLANs, and with MPLS, with the key idea being you can't ever see anything beyond your own LAN. Just remember that. That will save you wrong answers on lots of things. You can never see something other than your own, what's on your own LAN. If it's not physically plugged into your local LAN, you cannot see it, okay? Remember, at layer 2, you can't see it. And then we synthesized that web approach. There's more detail that they could have gone into in that story, but this one was pretty decent. All right, guys, we're going to continue on next time talking about multimedia and some wireless technologies. We have a lot of fun stuff still left to do, but this is a good stopping point for today, even though we do have the full 75 minutes this time. Isn't that ironic? The one day I do have it, and then they don't need it. So I'll wish you rest of a good week, and I will see you guys back in class in person on Monday. There's a decent chance I may have to broadcast that one remotely like this. So take a peek at the emails over the weekend. I'll send you more information on it. Let me look at chat. So Microsoft and Sync, yeah. Oh yeah, Microsoft does that. But you know what? So how would a server crash? Electronic failure. It has a physical failure. Everything that moves breaks, and that includes electronics as well. They fail sometimes because of radiation. There's radiation that passes through these systems, and it does break these things as well. What would the political aspect of this be? That was at 4:20. Political aspect, well, whether our president believes that global warming is real or not, companies do this to save money. So it makes good business sense. So that's a really good topic, but maybe we should talk about that live. I would love to hear you guys' thoughts on things on that. That's fun to talk about that. All right, have a great weekend. I'll see you on Monday. Bye, everybody.